Hello. This time we're going to explore the topic of binary relations and their graphical representations. And to begin with this, let me start with a definition. So let A be a set, and in that case, we say that a binary relation on A is a subset R of the Cartesian product of A with A. Now for this one, I want to provide several examples first. The first one. So let's say that A represents a set of people, right? And we have, let's say, Juan, Mary, and Diana. And well, here we indicate, for example, that Juan is a friend of Mary and Diana. But also we indicate that Diana is not a friend of Mary. And well, what happens in this situation? Well, we may be able to codify the information that we have here in the form of a collection, right? So in this case, I'm going to say that R represents the friendship relation. So we say that in this case, R corresponds to the following collection. You may say, well, look, Juan is a friend of Mary and Diana. So Juan is related to Mary, and Juan is related to Diana. We consider that friendship is a back and forth relation. So implicitly here, we would say, of course, we will have to say it, right? We say that Diana and Juan are friends, but also that Mary and Juan. But that's it. That's all that's all the information that we can collect. And what we can see here is that R encodes the friendship relation of the collection A. Right? Of course, we may say, just as an additional point, that we consider that this relation is symmetric. So immediately after this, right, this requires some definitions. And let me start in this fashion. We want to classify binary relations in a way that we can distinguish some of the properties. So for example, in friendship, there's an expectation that if you're a friend with somebody, that somebody's a friend to you, right? So I'm going to list a series of properties, and then we're going to exemplify them one by one. The first, let A be a set and R a binary relation on A. First, we would say R is reflexive if for each A in A, the pair AA is in R. In other words, a relation is reflexive where every member of the set is related to itself. R is symmetric if for each A and B in A, we have that A, B in R implies BA in R. So this is like good friends, right? If you say that A is a friend to B, then B is a friend to A. Unluckily, the love relation is not exactly symmetric, right? You may find situations where a person loves another one, but that other one doesn't love the original person. Right? Here's another property. We would say that R is transitive if for each A, B, and C in A, we have that A, B in R and B, C in R imply that AC is in R. Let's think in these terms. Suppose that A is a collection of stations connected with some public transportation. So we would say that any two locations are related whenever they're reachable using public transportation. That relation should be transitive, because if you can reach the point A to the point B, and you can reach point B to point C, well, then you should be able to reach A to C. Okay. And one more that we're going to consider, D. We're going to say that R is antisymmetric if for each A and B in A, if we observe that AB and BA are related, then we have that A is equal to B. In other words, you may say that the symmetry associated with this relation is very boring. You only encounter it when the elements are exactly the same. Okay, so what is that I'm labeling this in this fashion? The thing is that whenever we collect the following terms, I'm going to provide another definition. We say that R is an equivalence relation whenever it is, well, reflexive, symmetric, and transitive. We say that R is a partial order relation whenever it is reflexive, antisymmetric, and transitive. So look, I'm going to exemplify this using the following idea. Series of examples. And for the first one, I'm going to let A be the following collection of numbers. 1, 2, 3, and 4. And I'm going to indicate that two numbers are related. In other words, I'm going to define a relation on this set by saying I have two members, right, of A, only when we have this. X and Y have the same parity. Meaning they're both even or they're both odd. Well, let's see. Even though this is codified in this phrase, right, we can actually produce the members of this relation, because it's a small example. So we would say, well, is 1 related to 1? Yes, because the parity of 1 is exactly the same as the parity of 1. Well, also, 1 and 3 are related. Why? Because the parity of 1 is the same as the parity of 3. But similarly, I would argue that 3 and 1 are related because the parity of 3 is the same as the parity of 1. And, well, in the same token, I can say that 3 is related to 3 because the parity of 3 is the same as the parity of 3. And, well, I'll continue in this fashion, but you can see that I can say things like 2 is related to 2, 2 is related to 4, 4 is related to 2, and 4 is related to 4. Now, what we observe from this is that this relation is reflexive. Why? Because every member that we see here is related to itself, right? 1 is related to 1, 2 is related to 2, 3 with 3, 4 with 4. This relation that we have here is also symmetric, right? Why is that this is symmetric? Well, because whenever we observe that one thing is related to another, that another is related to the first thing, right? We see here, we, for example, see here that 1 is related to 3, 3 is to 1, and so on and so forth. The transitivity is also taking place, but it's a little bit hidden, right? For example, I can see that 1 is related to 1, 1 is related to 3, and then 1 is related to 3. Okay? Essentially, everything that you can complete in 2 steps can be completed in 1. Now, for this one, we may also introduce a graph representation, but this time I have to introduce loops and directed edges. So for instance, let's say that I group the members as 1, 2, 3, and 4. Now, whenever I see an edge, whenever I see an element like this, I'm going to provide an edge going from the first to the second. So in that case, I have to provide a loop. For 1 to 3, I will have to provide that one. From 3 to 1, I will have to provide that one. From 3 to 3, a loop. Well, from 2 to 2, a loop. From 2 to 4, a directed edge. From 4 to 2, a directed edge. And from 4 to 4, a loop. Now, in this case, we have an equivalence relation. Now, let me provide a second example. And this time, I'm going to set let A consist of the following set of numbers. 1, 2, 3, 4, 5, and 6. Just enlarge it a little bit. And I'm going to indicate, right, that 2 numbers are related whenever this happens. So I have x and y are related when x divides y. Once again, the example is small enough so that we can provide all, or we can enlist all the members of this relation. So we can say things like this. Look, well, 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 5, and 1 divides 6. Well, what else can I say? Well, 2 divides 2, 2 divides 4, and 2 divides 6. And that's it. That's basically everything that I can say with something starting on 2, dividing something else. Well, what else can I say? Well, I can say, for example, that 3 divides 3, 3 divides 6, and that's about it. What about the things that start with 4? Well, I can say 4 divides 4, and in this context, that's about it. What about 5? Well, 5 in this context only divides 5, and 6, well, only divides 6. So, again, I might be able to represent this using a graph, and I'll do it, right? So, all that I need is these 6 elements. So what I'm going to do is indicate 1 here, then 2 and 3 here. Then I'm going to place 4 somewhere here. Then 5 here, why not? And then I'm going to place 6 here. So what is that we observe? Well, first, 1 is related to 1. 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6. 2 with 2, 2 with 4, 2 with 6. Well, 3 with 3, and, well, 3 with 6. 4 with 4, 5 with 5, and 6 with 6. Now look, the diagram here that we have is a little bit cluttered. So we observe that this relation is a partial ordered relation. Why? Because it's reflexive, right? We observe this element, right, in the relation. It's transitive. Look, everything that I can complete in 2 steps can be completed in 1. And it is also antisymmetric. Look, whenever I observe an arrow between 2 different elements, I don't observe an arrow going in the opposite direction. So, what can I say? Look, whenever we have this, we may ignore the direction of the arrows and provide a much more transparent diagram, which is called a hazy diagram. Where we have an implicit direction of the arrows, and we understand that there is a transitivity involved. So in that case, the one that appears here at the bottom is 1. Then I will have a 2 here, a 3 here, and a 5 here, connected in this fashion. So I have 2, 3, 5. Then on top of those, I will have a 4 here and a 6 here. Then connecting those. And of course, I have to connect this as well. Since the direction is implied, and we also have transitivity implied, well, we save some of the arrows involved in the diagram. But now we can see why is that we call this a partial order, right? There is a certain ordering involved in the processes here, right? In the relation itself. It's not total because I cannot compare everything with everything, but I can compare some of its elements, right, with others. For example, I may say that 6 and 3 are comparable, but I cannot compare 6 and 5. But I can compare 2 and 6, but I cannot compare 2 and 3. Okay, so what about another example, right, of this type of relation? This time, I'm going to let A be the power set of the following set. So the power set of the set containing 1, 2, and 3. Now, this time, the relation in this set is going to be given by the following. This is the collection, right, of all those things in the product of A with A, such that X is a subset of Y. Right? Why is that am I able to say this? Well, simply because I'm dealing with sets, right? So I can compare them using this relation. Now, let's take a look at the following. Is this relation reflexive? Well, sure. And how can I demonstrate that? Well, in the following way. Let X be a member of A. Then, well, X is a subset of X. So, X comma X is in R. Okay, the relation is reflexive. is this relation, well, antisymmetric? Well, for that, I'm going to do the following. Let X and Y be members of A, and suppose, or assume, that X is a subset of Y, meaning that X is related to Y, and Y is a subset of X, meaning that Y is related to X. But look, these are collections. Whenever we have that X is a subset of Y and Y is a subset of X, then we can conclude that X is equal to Y. So now we can see that it satisfies the antisymmetry property. Lastly, I'm going to ask, is, well, this relation transitive? Well, for that, I'm going to say let X, Y, and Z be members of A. And assume that X is a subset of Y and Y is a subset of Z. Well, look, what we have here is the following. If I have an element that belongs to X, it also belongs to Y. But once it belongs to Y, well, it's here. So it must be there as well. Well, what do we conclude from this little argument? Well, hence, X is a subset of Z. And the relation is indeed transitive. So this is a partial order relation. And in fact, we can produce its Hayes diagram. You may say, how? Well, look, what should be at the very bottom of its diagram? In these things, we have to think about the minimal elements, so the elements that have nothing below them. Well, when we are dealing with sets, really the only thing that has nothing below it is the empty set. So that's the one that I put right there. Now I have to think on the next level. Well, on the next level, I should find all those elements that we would call the immediate successors of the ones at this level. Well, the immediate successors in this relation correspond to 1, to 2, and to 3. And then we place the diagrams, the edges, right? Because we are indicating a direction. Going up, things are going to become bigger in the sense of the relation. Well, what should be the immediate successors of the elements associated with 1, with the set that contains 2, and with the set that contains 3? Well, those would be the set that contains 1, 2, the set that contains 1, 3, and the set that contains 2, 3. And now we can see that 1 relates to this one. The set that contains 1 also relates to that one. The set that contains 2 relates to that. The set that contains 2 relates to that. The set that contains 3 relates to that one. And the set that contains 3 also relates to that one. Lastly, you may say, well, what are the direct successors of the members at this level, right? Well, really the only one that I can think of is this. 1, 2, 3. And for those, we impose that relation. Okay. So, here, let's try an exercise, right? Let's provide an example. Let A be this collection consisting of some symbols. And I'm going to impose the following relation. I'm going to say that this one is related to that one. This one is related to that one. And I'm going to say also that this one is related to that one. Okay, so let's test. Is this relation reflexive? Well, no. Why? Well, look, observe that this symbol belongs to A, while the order pair with the symbol doesn't belong to R. In other words, the pawn sign is not related to the pawn sign. Well, is this relation reflexive? I'm sorry, symmetric? Nope. This relation is not symmetric. You may say, why? Well, let's see. Note that this is in the relation. In other words, the pawn sign is related to the exclamation sign, but the exclamation sign is not related to the pawn sign. Is this relation transitive? Yes. But it is also anti-symmetric. Well, you want to think in graphical terms. Let's give it a shot. Let's see if we can diagram it. Right? So I have the pawn sign here. I have exclamation, and I have the interrogation sign. What I have is that, right? And also this. So to test for transitivity, right? We should ask, well, what are the things that I can complete in 2 steps? Well, there's only one thing that I can complete in 2 steps, going from here to here. And then you ask, can you complete that in a single step? Yes. For antisymmetry, well, what we should think is that whenever you see an arrow between different elements, you shouldn't see the arrow in the opposite direction. Well, look, these are the different, this one is related to that one, they're different, but I don't see the arrow going in the opposite direction. This one and this one are related, but I don't see the arrow going in the opposite direction. This one and this one are related, but I don't see the arrow in the opposite direction. So indeed, it is antisymmetric. So whenever you have a finite set and a relation, and a binary relation on that set, we can test for all these properties. We can actually produce algorithms to test them. Okay, so I hope that you enjoy it. Let me know if this is something that you would like me to continue on and explain in much further detail. And well, that's it for now. Take care. See you next time. Don't forget to subscribe.